Thank you very much for coming, everyone. Particularly thank you to the Cardano guys. It's very nice to have Charles here. My name is Asher Manning. I'm one of the developers at Zen Protocol. Zen Protocol is a decentralized platform for peer-to-peer finance, financial instruments, and financial applications. In order to have good financial applications, we need to have a high degree of security and a high degree of scalability throughput. We want to be able to run smart contracts as quickly as possible so that we can run as many of them as possible in per unit time. Today I'm going to be talking about how we're applying formal verification techniques, in particular resource verification, in order to improve efficiency and throughput on Zen Protocol. What is formal verification? Formal verification refers to techniques in software development to give strong guarantees of program correctness. This is distinct from something like unit testing or integration testing. In something like unit or integration testing, you're testing correctness in certain test cases, but you're only testing correctness for those test cases. Formal verification, you're testing for all possible cases. So a smart contract is a digital agreement between two parties. It's a piece of code that defines and enforces this agreement. Smart contracts can be used to implement financial instruments, decentralized autonomous organizations, prediction markets, decentralized exchanges, all kinds of things. There are probably applications that no one has thought of yet that smart contracts will end up being used for. And a smart contract can be any kind of program. People might want to do absolutely anything. This is literally an arbitrary piece of code. And this means that the properties of that program will also be arbitrary. And there are some properties which we really care about if we're doing decentralized systems, if we're having decentralized platforms. One of these is program runtime. So as we all know, there are some programs that run very quickly, some that take a long time to run. Some programs never finish running at all, they don't terminate. This can be a problem for us. The reason is that we need to come to consensus on the outcome of contracts. We need to know how long to run contracts for to be able to do this. If we're going to have consensus at certain intervals, we need to know what we can run within those intervals. So we need to know how long we're going to be spending running contracts. Can we know how long it's going to take to run a contract just from looking at it? There's this thing in computer science called Rice's theorem. And what it states is that for an arbitrary program, any semantic non-trivial property is undecidable. What this means is that if you're interested in some property of a program's behavior, of an arbitrary program's behavior, there's no way to deterministically figure out whether or not it has that property. A well-known case of this is the halting problem, where it's impossible to know, given an arbitrary program, whether or not it terminates. The same problem applies to program runtime or program resource usage. Given an arbitrary program or an arbitrary contract, there's no way to look at it and decide how long it's going to take to run. So how can we accept smart contracts? How can we have a smart contracting platform if we need to know how long contracts are going to take to run so we know how many we can run so that we can have consensus? But we can't look at a contract and know how long it's going to take to run. How can we do this? So there's two major approaches to the problem. You have Bitcoin, you have Ethereum, and we have our own solution to this. So I'll go over the properties of these solutions first, and then we'll dive deeper into how they work. So Bitcoin, it's possible to know the resource costs ahead of time, how much resources will be expended when running a Bitcoin smart contract. It's possible to execute Bitcoin smart contracts very efficiently. However, Bitcoin smart contracts are very limited and can't express complicated programs. In reality, we are often interested in complex programs, and that's what motivated Ethereum somewhat. In Ethereum, we can represent complex programs. However, we do not know the resource costs of programs ahead of time. Unfortunately, this comes with certain drawbacks, in particular that it's not possible to execute Ethereum contracts particularly efficiently. Zen Protocol's solution, thankfully, gives all three of these highly desirable properties. So in Bitcoin, you have a language called Bitcoin script. It's Bitcoin's smart contracting language. Now, Bitcoin script is intentionally restricted. It only allows you to write very simplistic, very basic programs. The reason it's restricted in this manner is because if you restrict a program, then in some cases of restrictions, it becomes possible to determine the runtime of a program before running it. Rice's theorem only applies to arbitrary programs. If you have a non-arbitrary program, a program with some restrictions, with the right restrictions, you can determine the runtime ahead of time. In Bitcoin, we normally consider the program runtime to be roughly proportional to program size, which is why in Bitcoin we're interested usually in block size, because block size is being used as a measure of resource consumption. For example, if I'm running a Bitcoin node and someone gives me a 1 megabyte block, I have a rough idea of how long it's going to take me to validate that block based on the block size. You can't do this in Ethereum. The block size in Ethereum tells you nothing about how long it's going to run for. That's why in Ethereum you have the analogous gas limit. So in Ethereum you have the gas model. Instead of trying to determine program runtime before running programs, in Ethereum we measure the program runtime, program resource consumption whilst we're running a program. So in Ethereum, there's some associated gas price to each of the operations that the EVM can perform. You can think of this as like a price list for all the different things the EVM can do. When a user wants to run a contract in Ethereum, what they will do is they will pay upfront for a certain amount of gas. We'll then go through the contract one operation at a time. For each operation, we'll look up the gas price and subtract it from the gas the user has paid for until either the program terminates or we run out of gas. If we run out of gas, then the program is going to fail, and you've lost your money that you just spent on running a contract for no reason. So accounting for gas is actually very inefficient. The EVM spends approximately 60% of its resources accounting for gas, just doing this, looking up the gas price of each operation and then subtracting it from the gas the user has paid for. Also, because we're executing this contract one operation at a time, because after every operation we need to check if there's enough gas left, we're forced to interpret the EVM bytecode, and interpretation is very slow compared to compilation. It's usually highly desirable to be able to compile programs. As an example for this difference in speed, if you run a game in, say, your browser, it's not going to be as fast or as sophisticated as something you can run natively on your computer. So in Zen Protocol, we came up with a very different solution to these two. So I'll explain how we got to this solution. We'll start by going back to the problem. Rice's theorem that all non-trivial semantic properties of a program are undecidable. What if we don't need to decide the resource usage of a program? What if someone already knows the resource usage of a program and they tell us, this is the resource usage, here's why. So they give a proof as to why their stated resource usage is correct. Now, it turns out we actually can validate a proof of resource consumption deterministically and efficiently. So in Zen Protocol, contracts are accompanied by proofs of their resource consumption. And this resource consumption can be parametric in its input. So you can very much write something that says, if the input to this contract is 0, then it'll take 1,000 steps. If the input is 1, it's going to take 4,000 steps. That's something you can absolutely express, you can prove it, and once submitted to the network, this proof will be checked. If it's correct, then we know how long the contract is going to take to run ahead of actually running it. So this is highly advantageous. There's no need to account for resource usage at runtime because of this. There's no need to keep track of gas like in Ethereum. We can also compile our contracts because of this, because we don't need to interpret. So you can get huge improvements in contract runtime and thus throughput. One of the important questions I'm sure I'm interested in is where did these proofs come from? How do we generate these proofs? So we take it's not possible in general to have some program that just looks at your input program and knows what the resource usage is going to be. There's no deterministic program that does that. However, because you're generating this proof off of the network, first we can accept some degree of non-determinism. So if you just want to do everything automatically, you can very much just run a proof search for ages, in reality not ages, usually a couple of seconds, and find the resource cost for your program. If you don't want to do that, you can also intervene manually in the proof search. Even for complex programs, we found very little manual intervention is needed. With good tools, good automated theorem provers, good SMT solvers, most of this can be done completely automatically. Developers don't really need to think so much about how these proofs are being generated. So to conclude, resource verification or formal verification of resource usage can give us great improvements in terms of efficiency and throughput. There's several other techniques that Zen Protocol has applied to get greater throughput besides just resource verification and the benefits that that gives. In Zen Protocol, we have first-class tokens, meaning that all tokens operate in exactly the same manner. There's no distinction of tokens like you have in Ethereum, where Ether is in some way a first-class token. It's exchanged through Bitcoin-style UTXO transactions, whereas everything else is an ERC20. It's controlled by some smart contract. In Zen Protocol, everything works like Bitcoin transactions. All tokens work like Bitcoin transactions, which means that you don't need a smart contract in order to transfer some token. So having first-class tokens gives you a couple of benefits. First, you can run smart contracts in parallel. This is exactly the same as parallel validation in Bitcoin. This gives great throughput improvements as well. Modern computers aren't really getting very much faster, but they're certainly getting more parallel. We can process quite a lot in parallel. So being able to leverage that is hugely advantageous. In comparison to other contemporary systems, for example, Ethereum is not able to parallelize. It's not able to take advantage of modern computer architecture, and it's forced to run single-threaded. The other is that because you don't need smart contracts in order to make transactions in some token, there is no first-class token like Ether. You don't need smart contracts to be online all of the time. You don't need them to be active. It may be that you need a smart contract to be active for some period of time to maybe set up a distribution, and after that, the tokens only need to be exchanged. So what we have in Zen Protocol is something called the active contract set, where contracts are active for a certain period of time. They can be reactivated and put back into the active contract set. Because only a fraction of the smart contracts on Zen need to be active at any period in time, this greatly reduces the burden on nodes, the amount of contracts that they need to hold in memory. And that's everything for the talk. So I can take questions. Yes?
I'd like to know a little bit more about these proofs. Tell me a little bit more about these proofs. What semantic restrictions do you have? What does the language look like?
So,
Lost over a bit.
So what these proofs actually are, they're SMT models. So what you have is a, unlike something like, say, Ethereum, where what you're actually submitting to the network is bytecode, in Zen Protocol, you're actually submitting a high-level language code. Pardon? No, it's not Turing complete, it's total, but this is a reasonable restriction. In reality, any smart contract that you're ever going to run is going to be total. No network can represent an infinitely looping contract because you'll never come to consensus over what it does. So you can't ever have Turing completeness in any kind of decentralized platform. The best you can ever hope for is totality, in that every program terminates. Yeah, so our language is a variant of F star, also very similar to Idris, but using an SMT solver to automatically discharge proof obligations. The advantage of that also is that the SMT solver can output models which can then be verified, which is what we're doing with the resource verification.
All right, so I can't use an American language. Actually, let's talk about the accounting model. Is it an extended UTXO model or is it an account model?
It's a UTXO model.
UTXO, okay. How do you represent state?
So state is stored on UTXOs. So some contract will lock its state on a UTXO to itself.
Okay. And what about data?
Pardon?
What about data, arbitrary data?
What do you mean arbitrary data? So like data attached to a transaction? Yeah, so a transaction includes a data field. And what contracts actually do when they're being invoked is that they take you're sending them a transaction skeleton, a partially completed transaction, and the contract will then fill in the remainder of the transaction. It'll take a partial transaction and create a transaction. So what you're sending to a contract is a partial transaction that includes the data you want to run it with.
Are there any restrictions on that model?
On the data that can be included.
Yeah.
So the data has a particular format, but other than that, no.
What about the oracles as far as data?
Pardon?
And what about oracles in relation to the
That was my
data?
next question.
Yeah.
What about the oracles?
What do you mean?
External data. So
External data, yes.
exogenous to the network.
So Zen Protocol does have its own Oracle solution. This would be to have oracles commit to sparse Merkle trees, so they can commit to large amounts of data in a very small commitment. Later, you can then publish the Merkle path, proving inclusion of some data within the commitment. So the way you do this is the oracles continually commit to large sets of data, but their commitments are very small. When you want to then prove that some data originated from an oracle, you then publish the Merkle path, and you can give a proof of inclusion in the data set that the oracle committed to.
Did you base the proof construction for runtime on anything like RAML, or what did you do?
No, do you mean the cost model?
Yeah.
So our current cost model is based on a paper by Danielson in 2008.
Okay.
I can't remember the name of the paper at the moment.
Was it a Popel paper?
Pardon?
Was it a Popel?
Yes,
paper?
it was a Popple.
Yeah, okay.
There are other cost models that could be applied to this. More or less any dependently typed cost model. So also something like McCarthy's 2016 model in his Coq library would be applicable.
It's pretty cool stuff.
Thank you. Does anyone else have any questions?
Yeah, I got a question. So is your language absolutely total? You can't work around that?
So it's a variant of F star, which is an effectful language. It does allow for effects like divergence. However, when we're accepting programs, we do necessitate that they be total. This is a very reasonable restriction.
Okay, so then what you're saying is that, okay, there is a certain subset of programs that you might wish to create, and as a result of it being a total program, the complexity of that program would become immense. So are you saying that there would be a certain subset of contracts which would be immensely complex, but whereas if you just introduce a little bit of Turing completeness, it would become simple?
No, there's no added difficulty in having totality. You can't. The only difference between Turing completeness and totality is that totality necessitates the programs terminate. Being allowed to express non-terminating programs is not.
Well, okay. So it isn't a Turing complete language.
It is a Turing complete language, but only total programs are acceptable.
Okay, so you're using a similar hack as what Idris is doing by sort of like using a similar concept of like gas, almost. This is what Idris is using.
No, this is not.
It's not the same gas as Ethereum gas. It's
No, Idris's gas mechanism also, F-star has a similar fuel mechanism. This is a different thing. This relates to how many unfoldings the type checker is going to do of a definition. Totality checking is not, it can partially be done syntactically. It's normally done based on a recurrence relation. In something like F-star, you can do it based on a well-founded partial ordering of terms. So if you prove that in every recursive call of a function, some metric is decreasing, then you've proven totality.
Okay, all right. You've answered my question. Thank you.
Yes. I can't hear you very well. Could you speak up? So at the moment, we're using Z3. However, I think we could use any SMTlib compliant SMT solver. Okay, thank you very much.